Recording. Yes, it started. Okay, this is our last presentation of this day, and our presenter is Helmut Simonis. And Helmut, I would say, a leading authority in decision optimization, in different techniques used for optimization. And what is interesting that he is not only well-known representative of academy world where he works right now, but he also he used to run company who created one of the first very powerful constraint engine. He is an expert in Prolog technique, but more importantly, he built so many practical optimization models that I always know if there are some very complex problem, talk to Helmut. He would always advise something what would be extremely valuable. And I really appreciate that Helmut agreed to make this presentation at Decision Camp. And so let's listen. Helmut.
Okay, thanks very much for the introduction. So I will talk about a problem that I encountered a few times in my working life on developing constraint applications, but never really paid too much attention to. And only in the last project, the last European project I worked on, this became came to the fore, and I had to think about this a bit more. It might be useful not just for optimization people, but also for just decision analytics people to understand that there is a gap there in our understanding. So it's about approximating a global objective by solving repeated subproblems. And we're using this for an open scheduling problem. And I'll talk about what that is in a moment. Okay, so we're actually looking at two different topics. On one side, we're solving a very specific industrial scheduling problem from the Assistant project, which was an EU project. We had the final review in February this year. But perhaps more interesting, we're discussing the general issue of short-term scheduling versus long-term objectives that we want to achieve. And there is a gap there in our understanding. Now, first, a little bit of a plug here. I'm from the Insight Center for Data Analytics, and here's a summary slide. So it's an Irish national center involving a number of universities where you have teams working on artificial intelligence. And it brings together basically all the expertise in the country. We have quite a lot of output here. So this is from August this year. We had a plenary session, and we were told that Insight had produced 3,900 scientific papers in the 10 years of existence. I have contributed very little to that, I'm afraid. We are involved in 135 European consortia. We have something like 400 PhD students that graduated as part of Insight. So this shows you can achieve, even for a small country like Ireland, you can achieve a lot by bringing together different teams working in related areas and trying to basically make a stronger working group by combining the expertise that you have. Okay, the research challenge I'm looking at is if you do optimization and if you do business management, you find that very often the long-term business objectives are not visible in the operational optimization problem or decision-making problem. And that is an issue because we spend an awful lot of time solving these optimization problems, but we don't really understand whether that helps us to improve the business objective in the long term. And we optimize the short-term objective, and we do that repeatedly, basically, let's say every day or every 2 hours. Every time we are solving a new problem, and we might solve that to optimality, but we have no idea whether that actually gives us a good outcome or not overall. So the research question is, what choices should we make in the short term to improve the overall result? Unfortunately, I don't have a fixed methodology that we can apply there, but perhaps some approaches that we might use and some techniques that we might play with. This is especially important when the future data is not yet visible. So we are making our short-term decisions without knowing what the next day will bring. And therefore, we can't, even if we wanted to, make a solution for the long-term problem because we don't have the information about that. We can, after the event, run an optimization program taking half a year's of data and trying to re-optimize that. But at that point, it's obviously too late. We don't know what we could achieve in the short term compared to that globally optimal solution, if we can actually find that globally optimal solution. And I was looking around a little bit, and this problem is rather rarely discussed in the literature in the optimization field. And I'll show you a few examples where things go horribly wrong. And the first example is production scheduling. This is what I'm doing quite a lot. And if you look at the literature there, well, nearly all scheduling benchmarks use the makespan as the objective. So the makespan says you want to minimize the latest end of any of the activities that you're scheduling. And here at the bottom, you have a schedule. This is actually from the Mood Thompson 1010 job shop. And here we have the result. We're starting at time 0, and the optimal solution has a makespan of 930. And this is what we try to optimize. So we know that there is no solution with 929, and there is a solution with 930, but that kind of assumes that there is no tomorrow. We are closing down the factory after we have run the schedule. And that's not really what's going on, because the next day you will have to solve a scheduling problem again. And part of the end of that schedule here that you have produced today will still be active when you run things. So you have to take that into account. So Cmax, the makespan, may not be actually the best objective for a production scheduling problem to deal with. Another example where it's perhaps even more obvious that something is going wrong is car sequencing. So this is a problem where you're putting cars with different options on an assembly line, and you have to mix the different options in such a way that you never overload the individual stations on the assembly line. So you can have certain options that you can have only in every second car or in 2 out of 5 cars or something like that. And the challenge is you have a mix of cars that have been ordered that you want to produce on the day, and how do we arrange that? And in fact, this is a classical problem. We wrote a paper on this in '88, which was one of the first examples of constraint-based optimization for this type of problem. And there has been a lot of work in this area after that. But if you look at the literature, one of the best strategies of solving this problem is to push the most difficult cars to the edges of the schedule. So you basically do them either at the start or at the end of the schedule. And this picture here actually shows a snapshot of the solution process where you have green values. You haven't yet decided on what you are going to do. And you're saying that you started in the middle and you're branching out, and you are still having some open choices here at the very end and at the very beginning of the schedule. This makes it easier to solve a particularly hard problem for a single day. But if you do this, then the next day you will have a problem, because these cars here at the end that you have made, that you have put there, make it very difficult to actually continue the schedule on the next day. So here's actually the optimization strategy, the heuristic that we're using to find solutions quickly, contradicts the idea that you actually have to make a schedule the next day as well. Another typical example would be personnel rostering. And this is an example here, quite old example, from a rostering system for TV and radio stations that we developed when I was still in France. So what is rostering all about? Well, you have to assign staff to shift patterns over a period, let's say, of 4 weeks. You want to satisfy the demand that you have in each shift, but you also have to satisfy the working rules that people have about weekends, about days off, rest periods, and so on. And again, if you schedule the solution for 4 weeks, this is okay, but the constraints actually apply on a rolling horizon. So if you have a solution here at the end of the 4-week period, it will interact with the first week of the next period that you're going to schedule. And if you treat these problems individually, then it's very easy to over-constrain the problem for the next period and make it very difficult to find a solution. Okay, and the last example that is much more recent. This is a system that I developed for an Irish company called NVD. About car transport, and you see here one of their car transporters. You are putting different cars on the transporter, and you deliver them from a compound or from a port to the car dealers situated in the country. So it's a very specialized transportation problem where you are building daily delivery tours, trying to optimize the cost. So on one side, you want to pack as many cars as possible onto that transporter. And as you can see, this can be difficult because you can tilt and shift these cars to pack them more closely together. You also want to minimize cost by taking routes that minimize the travel distance and the working hours. The distances, even in a small country like Ireland, are long enough, the locations are far enough apart that you are not doing this in a single day. And you're building tours where people start in the morning and make a few deliveries during the day and then end up somewhere in the countryside to have an overnight rest. And the question is, where are your trucks at 10 p.m. in the evening? Because that affects what you can do in the next day. And if you actually bring the cars back, the transporters back to your compound, you can start earlier the next day. You are more efficient there. Another thing you have to worry about is that you know which cars you want to deliver for the next day. You know much less about which cars you want to deliver the day after. And you have only very partial information about that. One of the problems that we were facing when building the tool was that the system would cherry pick deliveries for the Monday. It will do the stuff that creates the largest amount of profit immediately. So it will do a lot of local tours in Dublin or in Cork and not do a long distance trip to Donegal or Mayo in the west of the country. So you have only partial information, but you also should not be greedy doing the schedule in the beginning of the week, because that will just create more problems during the rest of the week. So all of these examples here are cases where, yes, we have an optimization problem that we want to solve every day or every time period, but the results that we obtain will affect the scheduling problem for the next time period. And if we make a mistake in solving the problem with too much of a focus on the short term, we may actually create more problems in the future and therefore overall do not deliver a good solution. Okay, what is the problem that we're actually going to look at here? It's from the Assistant project. This is an oven schedule for one of the industrial partners. So this is a scheduling problem where you have to schedule tasks on a set of ovens, and these are large industrial ovens, so I'll show you a picture in a moment. But you can think of it like a bakery. You're making different types of cakes, and they need an oven. You can put them in an oven, the cake into an oven. You can actually put multiple cakes into the oven if they need the same temperature profile over the execution. So you can share a task in the oven if they are compatible with each other. And that means they start at the same time, they end at the same time, and they use the same temperature profile. And you have conflicting objectives. So on one side, the energy use of the oven is very significant. You want to reduce the number of ovens that are used and when they are used. But you also have varying demand. So you cannot just use 5 ovens all the time. Sometimes you need 10, and sometimes you can actually work with 5. And if you're waiting for an oven to become available, this will affect the quality of the product. With the cake, I'm making cakes as a hobby, so this is something I'm well aware of for certain types of cakes. When you put them together, you have the dough ready. You have to bake them now. And if you wait too long, then the quality will be quite poor. One thing that was important in this particular problem was that the jobs are only visible when the previous process actually starts. And the previous process in this overall thing is a robot that is doing stuff on the compressor parts. This is currently solved by hand, and the industry partner expressed a strong need for change. They wanted to have an automated tool for this. Unfortunately, they only mentioned this halfway through the project when we already had made plans for doing other things. So this was a kind of a rush job to solve, and therefore we had to look at a cheap development solution, doing things quite quickly while still producing a good result. So what does this look like? This is an example of an industrial oven. So this is a walk-in kind of thing. This door here is really a door where you can walk through, and you can put multiple parts into that oven. It consumes a lot of energy when it is running, and you don't want to turn them on and off very often. You want to keep them running because then you can keep the temperature profile consistent. And this is the type of stuff that we're actually looking for. This is a compressor. These are the rotors in the compressor. And these things are heavy metal parts, but they're coated with all kind of clever technology. And that coating then has to be baked onto the part, and that has to dry as well. And you may have to repeat this several times. So one component of this rotor here may actually go through the oven several times while it's being produced. Okay, so what are we using to solve this problem? Well, this is an obvious approach for constraint programming, which is a declarative modeling approach for combinatorial problems, where you express problems in terms of variables and constraints. And in particular, for scheduling, we have over a period of 20 years, 30 years, come up with a set of global constraints that express modeling abstractions and provide quite powerful reasoning mechanisms. And some of these examples would be a disjunctive constraint, for example, which says that you have a machine and that machine can work on one task only at a time. Or you have a cumulative machine and you can do multiple things there, or you have a cumulative resource. You can do multiple things on that with that resource as long as you don't exceed the resource limit. Or you can have a constraint like global cardinality, which counts how often certain things occur. The nice thing about constraint programming for these type of problems is that it's compositional. So you can add constraints as required. You start with a very simple model, and then you actually add the constraint to see whether that still works. And you go along and add constraints as you discover them and evaluate what type of solutions can you actually build. So constraint programming overall, the main application areas would be for scheduling, also for rostering and transportation problems. But it's also used for things like test generation for software or hardware, for verification of compilers and of circuit. And another big area for constraint programming would be configuration problems, where you basically want to find a configuration where you have to choose which particular settings to use. And in fact, a lot of the Linux systems, for example, will have a constraint-based configurator to keep track of the different software elements that are installed and making sure that they're all compatible with each other. And okay, how do we approach this? Given that we have this overall problem and we have a data set which ranges over half a year, but in reality, we only see a day ahead or a few hours ahead into the future. So there is the data set that is given, but at every time point, we only see the data that are basically that have started on the previous machine. So we don't want to make decisions now that we have to regret later on. But we can't wait until we have more information, because we have to make some decisions now. Otherwise, we're never going to do anything. And the standard approach in optimization to deal with this is a rolling horizon decomposition. So you have the timeline here, and the data, this is now at the beginning here, the data close to now are quite certain, and you're aware of that information, you can get that. And the further you get into the future, the more uncertain the data is, or the more incomplete the data is. And what you have to do is you have to fix basically a look ahead horizon, saying, well, because the data gets more and more uncertain, I only take data that looks that far ahead, or data that becomes available up to this horizon time point. And then I'm going to schedule this. And then of that solution, I only take the first part. I only commit to the first part of the solution, and I ignore the solution that I have produced for the rest of that look ahead horizon. And when I come to the end of my commit period here, I basically restart. I will have more data that has become available, so I can again look ahead, schedule, commit to a certain period, and ignore the rest, and then roll through the time period like that. And obviously, the choice of how far ahead can we actually look, and for which time period do we want to commit, have a big impact on the solution quality. And by solving the problem, not just for the commit period, but for a longer period, we try to avoid the issue that I mentioned before, where we are creating a problem at the end of the schedule that we're looking at. The end of the schedule in this case here will be at this point here, but that part of the solution we're going to ignore anyway. So we are perhaps sidestepping the issue that we might create at the end of our scheduling period. So this is not a new idea. This is something that people have been doing for a long time, and largely, I think this is about the only way of approaching this. The issue is how do I know what horizon I can use? Does it make sense to spend a lot of time trying to improve my data quality so that I can schedule further into the future? And what time do I actually choose as my commit horizon? So do I plan only a very short period here, and then I have to resolve the problem very often? That may create a problem if you have to do some preparation work to get, for example, components from a warehouse to the assembly line. and make sure that all the material is in the right place before you start scheduling. So you may not want to make that commit period too small. Okay, so this is the overall decomposition, and that leads to a short-term scheduling problem. And normally, I would say scheduling, this is easy. We know exactly what we want to do with constraint programming. But this is the oven scheduling problem is one of the exceptions of the rule, and not just for constraint programming. The operations research people have the same difficulty because the oven basically breaks all the rules that you have in scheduling. So normally you say that one resource is working on one task at a time, and you can actually look how long will I need to run the resource to do all these jobs in a set of jobs to schedule. Because we can actually combine jobs together on a run, but not all of them, we have much less view of how much work is still left to be done. And we could, if we had a lot of time, build a global constraint to deal with this oven problem. And if we had a PhD student to do this for 3 years, we could probably do that. But in this case, we only had 2 months to actually come up with a solution for the customer. So we were not able to invest a lot of time and resources to develop a constraint. We can do a literature search, and there's basically one paper addressing this, a slightly simpler version of the problem by Lackner and others from Austria in Constraints in 23. And they have a quite complex optimization model where you have 2 scheduling models where you have variables that are linking these 2 models together. You have one model that is dealing with the jobs and the sequence of activities inside the jobs, and you have one model that deals with the machines and the tasks that you're running on the individual machines. Again, that was my fallback position, but I wanted to see whether you can do a direct model expressing the conditions of the oven as a disjunction of basic constraints. And that goes back a long time. We did something like that in the 80s and found that, well, okay, that doesn't work too well for a large-scale problem. But in any case, we need certain things, and if you want to understand the details, you have to read the paper. But I'll just say we have a number of jobs, and they go through multiple stages. We have tasks for each stage of a job, and these tasks run on machines. You can have, it's not a flow shop, you can have tasks of different stages compete for the same machines. All the machines are the ovens. You may use them for an early stage and a late stage of a process. There's no limitation there. You have release dates for the jobs that are given by the upstream schedule, by the previous activity. You have work in progress that is the result of the earlier schedules not being finished yet. You have machines and start variables for every task. So you have to decide on which oven do I put this and at which time do I run a task. You have precedence constraints between the tasks of each job. You have a waiting time when you have the job just waiting for a resource to be available. And then in this particular case, we're just counting how many ovens do we use. And we're taking into account the work in progress there. So we want to reuse ovens that are already active rather than starting up new ovens. And this may be a bit too technical detail for this audience, but you will understand these constraints here. We're just saying that if we have 2 jobs, 2 tasks of 2 jobs, then they are either on different machines, in which case they don't interact with each other, or one is starting before the other, or it's the other way around. And that is the basic decomposition of the disjunctive machine choice constraint. So here we have a set of machines, and each machine itself is disjunctive, so it can only work on one job at a time. And this is the case for where we have this constraint for every pair of tasks that cannot share the oven. And if we want to extend that to handle the case where they can share the oven, we have to check that they have the same profile, and these are these type variables here. And then we're saying, well, they are on the same machine and they start at the same time, and therefore they also end at the same time because the type is the same. So this is a very easy way of expressing this oven condition. The only problem with this is that we can now put a lot of tasks into the oven at the same time, and the oven has a finite capacity. And in fact, for this compressor oven scheduling problem, we have only the capacity to put two activities, two tasks in the oven at the same time. So we'll have to do something more complicated. Yeah, this is nice if you're interested in constraint programming. Otherwise, we are basically just counting how many jobs share stage J with job I, and we are then saying that the total number of jobs that share the oven has to be less than this max stacked value. Okay, as I said, the details here are not that interesting, perhaps. But the first thing was that I basically only wanted to do that as a baseline solution, because from my past experience, I thought, well, this is not going to work. These decomposition models don't work that well. This is why we have these scheduling constraints in the first place. So it definitely will not scale to 1,000 tasks or 10,000 tasks, because you have a quadratic number of constraints that you're producing between the pairs of tasks that you're looking at. But technology improves, and some of the more modern solvers, SAT-based solvers like Chuft or CP-SAT from Google, actually work with this model very well. And MIPS solvers work with the model reasonably well as well. More traditional scheduling solvers like CP Optimizer from IBM don't like this at all. This depends on the technology that you're using to solve the model. And there is a size limit that you have to respect. But for our particular case, it actually does work quite well. And you have three elements of the objective. And again, the details are perhaps not that important. We have different weight factors here. On one side, we have the total waiting time of the jobs, and we have the number of ovens that we're using in the schedule, and the number of tasks that we're stacking together that are reusing the oven. And these three things, each of the elements are nice things to actually to improve. So obviously we want to minimize the waiting time that is required. We want to minimize the number of ovens that we're using, and we want to maximize the number of tasks that are stacked together. So we will have a negative coefficient on the alpha 3. But if we want to reduce the waiting time, then we will need more ovens, because we will need an oven ready anytime a task becomes available. And if we stack more things together, then at least one of the tasks that we're stacking will have to wait until the other task becomes available. So these are conflicting, all three, with each other. And it's not obvious what compromise we can actually find that overall improves this for an arbitrary choice of these coefficients alpha 1, alpha 2, and alpha 3. And here we have a visualization of these short-term schedule. This is a job view. So each of the lines here of the Gantt chart is a job. The red part are the activities that are outside our scheduling problem. These are the tasks on the robot. They define when the components will become available. And then we have two stages in our case here. We have a curing stage and we have a trying stage. And the darker color means that we're stacking things together. So we are stacking, for example, these two jobs together, both for the curing and for the trying stage. And here we see that we have to wait for this job here until that job becomes available so that we can put them together. If we actually want to run this job earlier, then we can no longer stack them together. And we may also have a waiting time here where we basically just wait until another oven becomes available for reuse to avoid starting up another oven. And here we have our look ahead horizon, and here we have our commit horizon, and only the things which are outlined in blue are the parts of the schedule that we are going to commit to. So these are the things that we're telling the operators, you are going to do that. And so you're going to wait until that job becomes available to actually stack these together. And you're not waiting for these, you're actually going to run those. Here we are kind of committed to stacking these tasks together, even though they're outside the commit horizon, because we're still saying that we are not actually starting that activity now. This is the machine view, the resource view of the same schedule. So we have our resources here, and we have the task where we're seeing in create a work in progress. So these are the activities from the previous run that are still running. And these are the things that we are scheduling now. And again, we have the look ahead and the commit. And these are the activities that we're going to actually commit to. And you can see that we're basically reusing the ovens that were already active. We're not starting up another oven, and that would increase the energy consumption significantly. Okay, so the first question is, we have defined our short-term solution. Is that actually a good short-term solution? And even with our basic model, we solve many of the problems to optimality. That depends a little bit on the solver that we're using. And in overall, we find that the optimality gap is very, very small. And we can increase the search time a little bit, and that will help find more optimal solutions. But basically, we are doing pretty well on solving these short-term solutions. But are we optimizing the right thing? So we have optimal solutions for all our short-term solutions. Does that give us a good overall solution? Well, here's the long-term schedule. So here's what we obtain as the schedule over a period of a month, I think. And each of these little bars here are individual tasks that we have scheduled, one after the other. And we see that we're using basically all of the resources at some point. That is actually a preference by the customer saying, I don't want to use the same oven over and over again, because then I will clock in a different number of hours of operation on the ovens, and some of them I will have to repair or replace earlier than others. So they want to spread out the utilization of the different resources, as well as making sure that you're using the oven for a longer time period. And you want to avoid situation like this one here, where you're basically running two tasks on an oven before you didn't use that, and after you're not using that. But okay, at that time, there's a lot of demand, you need a lot of resources. And once that demand peak is over, you can shut down some of the ovens again. So although this looks quite horrible, at certain periods of the scheduling horizon, this may be unavoidable just because you have so many orders arriving at the same day. You can abstract the machine runs into a concept which is actually called machine run, where you ignore very short shutdowns of the resources and only keep basically you're merging all these runs, and this is when the oven is actually operating and consuming energy, and when it's not consuming energy, you have the blank space. And that is a schedule for the whole months. But yeah, just looking at the schedule, you see that lots of things actually are quite nice, but you have really no idea whether this is a good or a bad schedule, and whether an alternative would be worse or better. So the thing to do is you define your KPIs. They are not actually part of the model itself, but there are things that you can compute once you have a solution. And there are simple things like the global time needed to actually produce the solution, or the number of jobs and number of tasks. Hopefully that is the same for every solution. And you're checking what's the percentage of the sub-problems that you're solving to optimality. How many tasks can you stack together? What's the percentage of tasks that you can stack? Or how many jobs have no waiting period and therefore have the highest product quality? And the number of ovens used. And you have quite a few other KPIs. They are all useful, but if you talk to the different people in the company, they will all put different preferences on what is more important than the other. So it's not clear that you can just rank the KPIs or compare the different values in a straightforward way. But once you do that, you can run experiments. And this is what we were doing basically to understand what is the impact of the look ahead parameter. So we're trying looking ahead 4 hours, 6, 8, 10, 12 hours, while keeping the commit horizon to 4 hours. And obviously, the more time you look ahead, the more time the solver will need to come up with solutions. You can see that the number of sub-problems that you solve to optimality does increase a little bit from, let's say, 65 to 70%. The number of stacked tasks actually reduces a little bit because of the weight factors in the objective function. If you have a longer look ahead period, it can actually decide it's better not to stack some task if that reduces the waiting time and the number of ovens that are going to be used. But overall, you see that a lot of the KPIs are not really affected by that look ahead parameter in a meaningful way. This is somewhat different if we look at the commit horizon and again change that from 1 hour to 8 hours. As we actually increase the commit horizon, we are creating fewer and fewer sub-problems, so the computation time improves dramatically. But what we can also see is that for some of the objectives, some of the KPIs, there's not that much of an impact, but some of the values like the overhead percentage is going up quite dramatically. So you are much better off with a short commit horizon rather than a longer period. And this only when you actually increase the commit horizon and the look ahead to 8 hours, you're actually getting an improvement again. And the number of oven runs per oven is also going to decrease as you as you increase the commit horizon. So you can use basically these KPIs and these plots of the KPIs to compare different solutions and see what is going to happen. So yeah, is that solution that we are producing really good? Well, we can compare it to other solutions that we are producing. We are scheduling with limited information, and we can therefore not expect that we are finding the globally optimal solution just by looking at shorter time periods. So there are three things that we can try and improve. There is a process challenge where we can actually have a look on whether we can improve the data visibility. Can we actually get more information available earlier? And for example, not when they finish the task on the robot, but when they start the task on the robot, can we actually get that data then for our scheduling? And that would help by improving our visibility of the data. There's a modeling challenge. Can we define a short-term objective or the parameters of our objective function that produces better long-term solutions? This is not something that is easy to do. We basically here have a simulation paradigm. We are basically using a digital twin to simulate what the factory will do over a period of time. We can't actually run these experiments for half a year with the actual factory. And the data points that we will get from the actual factory are very, very limited. So we cannot actually do much machine learning on this. And we have an algorithm challenge. We can at least try and understand how far are we away from the global optimum. If we had all the data available at the very start, could we build a schedule that solves that to optimality? And that will require quite a powerful reasoning algorithm. So this is not something that we are doing at the moment. Okay, so this was the overall idea. We have a problem of this oven scheduling. If you want to know more about this, there is a paper on this problem that I presented at ModRef 2 weeks ago. If you are interested in constraint programming and you want to learn about constraint programming, I've worked with a colleague from Georgia Tech on an overview of the teaching methods for constraint programming, and there is a preprint of that available. And recently, I've also worked on a survey of constraint programming and scheduling, and again, a preprint is available on that as well. And from that survey, I just want to show you two kind of pieces of information. This is a plot which shows the number of papers on constraint-based scheduling that appear every year. And you can see we are now in 23, we had something like 60 papers in that particular field. Okay. This is nice that it is improving. It's also a problem that there are all these papers. Are they any good? The survey does some interesting things. If you're interested in a particular application area, it will have different keywords. There's an ontology that we have defined, and it will tell you which papers actually are most relevant for these application areas, and this is automatically derived from the works by extracting basically occurrences of the ontology terms in the papers themselves. Okay, if you still want to know more about this, I'm going to run a training course on constraint-based production scheduling in November. This is part of the entire project. This is, if you are in Europe, you may have heard about this. There's the European Digital Innovation Hubs, where you have regional training facilities where we are part of the Munster region in Ireland, where the Commission is trying to make a lot of the AI tools, a lot of the modern technology available for SMEs and the public sector that are lagging behind, let's say, the multinationals in the use of these things. And Entire is our project here with the partners here. And of course, I would be amiss if I didn't mention Enterprise Ireland, which is funding the whole thing for us. So a 2-day course in November with the modeling focus and a link there. Unfortunately, if you're outside Ireland or if you're part of a large multinational, then you'll actually have to pay for that. But if you're as SME, you can get basically the commission pay for you to be trained on this, which I think is a nice initiative. Okay, so what were we doing? We were looking at the non-standard open scheduling problem from industry and had a look at some decomposition of the resource constraints. We have pretty good short-term solutions, but we still don't really understand how close are we to a global optimum. And we don't really have a good methodology for doing this, except build a digital twin and run lots of simulations to find out what is going to happen. Now, in any case, the industry partner that we worked with was happy with the solution and with the analysis. So in that sense, it was a success story, even if we have some open questions rather than just a fixed solution. And I think that's it.
Okay, thank you very much, Helmut. And I understand it's end of the day, people tired, but let's see if you have questions. No? Okay, just applause. I just want to make a few comments. Not everybody deals with these problems, especially in our business decision management context. But if you think about these problems, you will see that our new AI tools that don't deal with constraint solvers or linear solvers don't even touch these problems. And if you look on different classification, it's far beyond of modern AI capabilities, but it's certainly constraint programming and solves scheduling problems for years, and has a lot of success stories. And so this is certainly very interesting area. I just can add from real world because I was lucky to participate to solve these problems for years. For example, we had the largest, one of the largest warehouse in the United States, in Pennsylvania, and we built system for them that loaded trucks. And every day they had limited fleet of trucks, and they scheduled based on current orders 40 to 100 different trucks to send in everywhere in the United States. And if we did very optimal solution, if you find very optimal scheduling solution, assignments of orders to trucks for one day, then we really suffered on another day. It was very optimal, but we already used very important trucks. They all have different capacities. And so we certainly always deal with this short-term optimization versus long-term objectives. This is very practical problem. The same thing when we do scheduling of people, when you send different teams of people to different locations. So it's always about scheduling for first few days, but considering the whole horizon for probably 2 weeks and be ready for rescheduling the next day. All these problems very, very practical, and I feel like Helmut gave us very good overview of what's available, and I just while I'm doing this, I learned something what I'm going to apply to current system, what we right now deal with. And this is a movie scheduling, different scenes. And I think it's based on what I heard, we can improve schedule essentially. So Helmut, thank you very much. And this is the end of our first day. You can see tomorrow's schedule. It starts at 9 o'clock. we had today so many absolutely different presentations, and this is probably beauty of this event when we have people with different experience and touch different areas, but all together they have a nice term that combines us. Today it's decision intelligence. Maybe in the future it would be something what Alan Fish mentioned about knowledge modeling, but this is knowledge modeling oriented to very practical real world problems. And if you don't have any other questions, or anybody has questions or comments? Not? Okay, so let's call it a day, and we will see you all tomorrow at 9 a.m. Thank you very much to all presenters and all attendees. We will publish these presentations tonight. Bye. Have a great evening.
Okay. See you tomorrow.